Hello everyone, welcome to Reactify Labs. In this video, we will talk about coordination services. As the name suggests, we are going to talk about the services which help in the coordination between the nodes. So let's start with the technical definitions. Coordination services refer to specialized components that facilitate communication and synchronization among distributed system nodes. So coordination services refer to specialized components that facilitate communication and synchronization among distributed system nodes. They play a crucial role in achieving consensus. They play a crucial role in achieving consensus and managing distributed transactions. And ensuring cooperation among components. Cooperation among components. So, coordination services play a crucial role in achieving consensus. What is consensus? Consensus means voting, means agreement upon a particular value of a particular data, right? What are the key elements of coordination services? First one is consensus algorithm. Consensus algorithms. Coordination services often employ consensus algorithms like Paxos or Raft for decision making among different nodes. I have talked about Raft in a previous video. Please go and watch it if you don't know what Raft is. Okay. Next one is locking mechanisms. Locks are used to synchronize access to shared resources, preventing conflicts in distributed systems. And third is transaction management. Coordination services assist in managing distributed transactions, ensuring atomicity, consistency, isolation, and durability. Let's talk about some of the consensus algorithms in brief. Consensus algorithms. First one is Paxos. So Paxos is a consensus algorithm that plays a pivotal role in coordination services, ensuring that distributed nodes reach an agreement. In Paxos, distributed nodes collaborate to agree on a single value even in the presence of faulty nodes. Paxos operates through three main phases: prepare, accept, and commit. So these are the three main phases of Paxos algorithm. Each phase contributes to achieving consensus. The algorithm includes a leader election process, designating a distinguished proposer responsible for coordinating agreement among nodes. Second is Raft. Raft is another consensus algorithm known for its simplicity and clarity, making it a popular choice in distributed systems. Raft employs a leader-follower model where one node, the leader, manages the replication of logs across the distributed network. Raft ensures consistent log replication across nodes, ensuring that all nodes have an identical log of commands. Raft's leader election process ensures fault tolerance by promptly electing a new leader if the current leader fails. Okay. Now let's talk about the locking mechanisms. Locking mechanisms. So first one that we are going to talk about is centralized locking versus distributed locking. In centralized locking, a single lock manager oversees the coordination of resources. But it has some drawbacks. First one is the single point of control, right? If it's a single point of control, it means it's a single point of failure and it can be a bottleneck. Centralized locking places the responsibility of managing locks on a single entity, often leading to a single point of control for the entire system, and hence scalability concerns. This model encounters scalability challenges as the system grows, potentially becoming a bottleneck for resource access, right? But in distributed locking, contrast to what the centralized locking is, distributed locking spreads the responsibility of managing locks across multiple nodes. Decentralized control is provided by distributed locking. By decentralizing lock management, distributed locking distributes the load and offers better scalability, especially in large and dynamic environments. And it has enhanced fault tolerance. Additionally, distributed locking enhances fault tolerance as the failure of single node does not cripple the entire locking mechanism, right? So, centralized has the problems like single point of control and scalability concerns, whereas distributed has decentralized control and enhanced fault tolerance. Right? Next, consistency challenges. Consistency challenges. So, maintaining consistency across distributed nodes poses notable challenges, emphasizing the pivotal role of robust lock managers. Concurrency concerns are there. In distributed environments, concurrency introduces complexities, ensuring that multiple nodes access shared resources in a coordinated manner. Addressing consistency challenges involves considerations for transaction atomicity, ensuring that operations either fully succeed or leave the system in a consistent state. And there are some roles that lock managers also play. Robust lock managers, whether centralized or distributed, play a crucial role in addressing these consistency challenges. Okay. They implement concurrency control measures to regulate simultaneous access to shared resources, preventing conflicts and ensuring orderly operations. Incorporating transactional support, lock managers contribute to maintaining the integrity of distributed data by providing a reliable foundation for coordinated transactions, right? So, locking mechanisms have consistency challenges and scalability challenges as well, which are addressed by distributed locking. So, basically, what we see, centralized locking and distributed locking. Centralized locking does not have consistency challenges, but it has scalability challenges. Distributed locking does not have scalability challenges, but it has consistency challenges. So we need to make a trade-off between these two and balance the consistency and availability. Okay. Now let's talk about the use cases. So the use cases of coordination services. So first one is distributed databases. Coordination services play a pivotal role in distributed databases. ensuring consistency, fault tolerance, and effective management of distributed transactions. Okay. So, uh, what are the problems that come? One thing is consistent state. Coordination services maintain a consistent state. Okay. So consistent state problem might come in distributed databases because obviously the data is distributed, different nodes, communication over the network, communication delay, communication overhead, for faulty network, node failures, different things can come, right? So coordination services maintain a consistent state across distributed nodes, contributing to the overall reliability of the distributed database and fault tolerance. The coordination of transactions includes mechanisms to handle failures, ensuring data integrity in the event of node crashes. Next is microservices architectures. In the context of microservices architectures, coordination services contribute significantly to maintaining the consistency across distributed components. First one would be services coordination. Coordination service Coordination services help synchronize actions and data updates across microservices, ensuring a coherent system state and transaction integrity. They aid in managing distributed transactions seamlessly in a microservices environment where services may be geographically dispersed. So even if the services are geographically dispersed, still the integrity of the transaction is maintained, even though there are consistency challenges. Okay. Now let's talk about some of the other challenges. First one is consistency versus availability, which is always the challenge in any distributed system. What do you prioritize? Whether you prioritize consistency or you prioritize availability. In coordination services, one of the central challenges is striking a balance between consistency and availability. Okay, this balance needs to be delicate, or like, see, if this is the scale of consistency and availability, you need to balance it in the middle exactly, to according to your needs, what kind of consistency or availability you need, right? So emphasizing strong consistency ensures that all nodes in the distributed system share a uniform and up-to-date view of the data. Prioritizing availability allows nodes to continue functioning even in the presence of network partitions or node failures, potentially leading to temporary inconsistencies. So, if we prioritize consistency, availability might get compromised. If we prioritize availability, consistency might get compromised. So, this is where we need to take a call depending on the use case of our system, what kind of problem we are solving, what kind of consistency do we need, what level of availability do we need, and depending on that, we should try to balance these two. Okay. Next is scalability concerns. As coordination services scale up to accommodate larger system sizes, a set of challenges emerges that demands careful consideration. The growing number of nodes in a distributed system introduces complexities in maintaining efficient coordination. Scalability concerns involve addressing the heightened network overhead and communication load that accompanies the proliferation of nodes. So, if there are more number of nodes, increasing number of nodes, then there will be more communication, then and hence there will be more network overhead, right? So, two nodes don't take a lot of resources, but if there are multiple nodes and using the what do you say, permutation and combination, different nodes make contact or exchange information with different other nodes, this is going to increase the network overhead significantly. So that's why scalability challenges come. Let's talk about some of the real world examples of the systems which use coordination services or which help the other systems employ their coordination services. Real world examples. First one is One of the most popular is Zookeeper. So Apache Zookeeper, renowned for its coordination capabilities, is instrumental in diverse scenarios within distributed systems, like distributed systems coordination. Distributed systems coordination. Zookeeper excels in maintaining synchronization and coordination across distributed systems, providing a reliable foundation for various applications. Next is configuration management. Serving as a centralized configuration repository, Zookeeper ensures that all nodes within a distributed system share consistent configuration settings, enhancing system stability. Next is leader election. Its robust leader election mechanism is crucial in scenarios where designating a leader node dynamically is necessary for efficient task distribution. Right? Next is, let's talk about the consistency model of Zookeeper. So Zookeeper's unique consistency model reinforces its reliability and uniformity in managing distributed data. So its consistency is sequential consistency. Zookeeper guarantees sequential consistency where all nodes observe updates in the same order, fostering a dependable and predictable distributed environment. Also, it provides ACID properties. Upholding ACID properties, Zookeeper ensures atomicity, consistency, isolation, and durability in its transactions, thus mitigating the risks associated with distributed data manipulation. Next, another example is etcd. It is a distributed key value store, right? So etcd is a versatile distributed key value store which plays a pivotal role in coordinating activities within dynamic environments. So it is a distributed key value store. It provides container orchestration, so integrated with container orchestration systems like Kubernetes, etcd facilitates the coordination of container related data, ensuring seamless deployment and management. Next is atomic transactions. Its support for atomic transactions guarantees that operations within etcd either fully succeed or leave the system in a consistent state, a critical feature for maintaining data integrity. We all know about atomic transactions, right? Either everything will pass or nothing will pass. Okay, let's talk about the consistency and reliability of etcds, and that will be the end of this video. etcd's commitment to providing consistency and reliability positions it as a trusted component in distributed systems. So it uses raft consensus algorithm. etcd employs the raft consensus algorithm, reinforcing its reliability by ensuring fault tolerance and consistent replication of data across distributed nodes, and quorum based operations. The use of quorum based operations in etcd ensures that a majority of nodes must agree on updates, maintaining a consistent view of the system even in the presence of node failures. I have made separate videos on both raft and quorum. If you have not watched it, please go ahead and watch it, and that will help you clarify what raft is, what quorum is, how they are different from each other, and how they are used and what problems they solve. Okay, so that's all. I hope this video helps you get clarification on the coordination services and how they are used, why they are used, what are the different types of coordination services, and what problems they solve, in what manner they solve the problem, what is centralized locking, what is distributed locking, why one or the other, and what are the drawbacks of centralized locking, why distributed locking is preferred even though it is complex. So a lot of things I covered in this video. I hope you like it. So I hope this is helpful for you more than you like it. So thank you for watching. Please remember to like, share and subscribe. I will see you in the next one.